The goal of this talk is to illustrate how to adapt a specific dataset and to design the pipeline to solve a ranking problem in a real-world scenario, explaining step-by-step the approach and the implementation part. So I will start by declaring the problem statement. Then I will explain you in details the most important part, that is the data preprocessing, to understand how to model and manipulate features in order to create the proper input data set tailored to the machine learning algorithms requirements. And then I will show you the model training part, the library used to create the model, and finally the result obtained. So this is our problem statement. So how to create a learning to rank pipeline using the Spotify dataset available on Kaggle about the worldwide daily song ranking. This is an internal project, began during the Sease company meeting held in September as part of the machine learning hackathon. Despite the many inspirations suggested on the Kaggle website, the objective of the Sease hackathon was to adapt this dataset to a learning to rank task. So this presentation aims to illustrate how to set up and build a learning to rank system, starting from the available dataset, then creating and manipulating the training set and the test set, and then training a ranking model with a certain accuracy using open source libraries. What is learning to rank? Learning to rank is the application of machine learning in the construction of ranking models for information retrieval system. The difference from the traditional machine learning is that in this case, the training set consists of list of items, documents, and the aim of the learning to rank is to come up with optimal ordering of those items with respect to the query. So the key challenge of applying learning to rank is to define relevance. Each item, document, is composed by a query ID, and each query is associated with one or more documents. Relevance rating that consists in a relevance grade that should be non-negative integer starting from 0, where the larger the number, the more relevant the document is. And then the feature vector that is composed by n features ID value. Before telling you our approach, first of all, I want to briefly describe the dataset and its features. So dataset is about the daily ranking of the 200 most listening songs in 53 countries. It spans over the period from the 1st January 2017 to the 9th January 2018. It contains more than 3 million rows. As you can see from the table, there are several features. The first one is the position on charts of the song. The second one, track name, is the title of the song. Then we have the name of the artist, number of streams. Then we have the Spotify URL. We have seen that it can be used as a univocal value of the song. Then we have the date of the chart and the region. So the country code, since data and metadata has been collected from the Spotify regional charts data. So during the exploration of the dataset, we began to brainstorm and generate ideas to understand how and which techniques were most appropriated to achieve our goal. So what was our approach? We know that learning to rank links machine learning into the search engine. So we have supposed Spotify internal search engine, where is integrated a training ranking models. And in this case, documents are the song. The query is a search for one of the region of the country. The relevance rating is estimated from the position on chart, and feature vectors is composed of all the other n features. So the search engine take in inputs the region, so the query issued by the user. The best result from that query are passed into the ranking model and reordered before being returned to the user. So the model is able to return a re-ranking of the song based on their relevance to the query. Let's start now with the most important part of the pipeline. For best result, data preprocessing is a crucial step, as the raw data must be transformed into a format suitable for machine learning models. Before going to details of data preprocessing, it is better to clarify the features level. I mean that in learning to rank, features can be distinguished in 3 different levels: document level, query level, and query dependent. Document level describe a property of the document, so the value depends only on the document instance. Query level describe a property of the query, so the value depends only on the query instance. Query dependent features are an intersection between the two. So in this case, describe a property of the query in correlation with the document. In our case, document level features are track name, artist, and streams. Query level feature is the date and consequently day, months, and weekday. In our case, we do not have query document features, but potentially they could be implemented in the future as further study. That's why I want to mention them. One could be the matching query region title language. So we can check the correlation between the country and the language of the title, estimated from the song of the title of the song. And the other, matching query region artist nationality. So to check the correlation between the country and the nationality of the artist, estimated from the artist name. We start now with the data cleaning. That is the process of ensuring that our data are correct, consistent, and usable. In particular, we verified the completeness of the data, and we found a total of 657 not an object in track name and artist features. Since this data was already present in our dataset, for example, in our query, in our list, as you can see in the table on the side, we decide to handle the missing value and fill them by creating a dictionary, where we have used the univocal ID of the song as key and the title song name as value. If you remember, we use as univocal ID the URL encoded as an enumerated type. The same thing was done to fill all the rows containing missing values in the artist column. Moving forward, feature engineering part is vital and must be performed to choose the right features in the right format by transforming them or creating new input features. There are several techniques: feature selection, feature extraction, feature transformation, feature importance, with the aim of preparing the proper input data set and improving the performance of the machine learning model. Most of the machine learning models, algorithms, are not able to handle non-numeric data. So we have to find a way of transforming them into numbers, applying categorical encoding. Therefore, there is no single answer on how to approach this problem. And we were faced with the challenge of understanding how to transform these kind of features into suitable numerical values. So now let's see one by one the structure of the features and the approach we decide to undertake to solve this problem. The first feature is the position. This variable was chosen as the target variable and used to estimate the relevant rating. As mentioned earlier, relevance label should be non-negative integers starting from 0. So using the position values as relevance label may not be appropriate. As you can see, the position level range from 1 to 200 and may not, and it may be too high and misleading for the model. So we decided to group the position value and make a sort of mapping in 2 different ways, creating a relevance label from 0 to 10, as you can see in the ranking column, and another approach creating a relevance label from 0 to 20. And then we checked the difference between these 2 variations in the model performance. we try to keep a finer grain on the grouping of the most relevant values. In fact, as you can see, the song in position 1 has relevance 10, the song in position 2 has relevance 9, and so on until the song in position 131 to 200, which all have the same relevance, 0, because they are not as important as the top position. Then another feature, the track name. This is a document level features. We decide to encode this variable using two different approaches, hash encoding and doc2vec. And then we made a performance comparison between these two techniques to see what changed and which performed better. Feature hashing maps each category into a category feature to an integer within a predetermined range. So it's a fast and space efficient way of vectorizing features by applying a hash function. To do that, we have used a library called category encoders. And as you can see from the example code, the main argument of the function are calls, where we specify the column to encode, in our case, the track name. Then we need to fix the dimensionality. So we used the default value that is n components equal to 8. And then the central part of the hashing encoder is the hash function, which is specified with hash method. By default, the value is the algorithm ND5, but a user can pass any algorithms of his choice. This function maps the value of a category into a number, and it will take a string and return a number between 0 and n-1. So in our case, from 0 to 7. And these hash values are used as indices directly. So if you can, in fact, you can see that the track name features was replaced with 8 new additional columns, from column 0 to column 7, which contain binary values, either 0 or 1. Then doc2vec. Doc2vec is an unsupervised learning that represents each document sentence as a vector. The algorithms is an adaptation of word2vec, which is one of the most popular technique in natural language processing. Doc2vec, as word2vec approach, use deep learning and neural network-based techniques to compute features vectors for every document sentences in the corpus. The only difference between word2vec and doc2vec is that another feature vectors named paragraph ID need to add with the model architecture. To do that, to apply this technique, we use the Python Gemsyn library. Then, first of all, we have to replace sentences as a list of words. These sentences are converting into a training corpus of tagged document consisting of two parts, tokens, so a list of words, and relative tag, as you can see in the picture, tagged document. For simplicity, for each document, we only assign a unique integer ID, and is a good practice using the indices of sentences as the tag. In fact, for example, tag 0 is related to the first song of the data set, tag 1 is the second song of the data set, and so on. Then we created the vocabulary, that is a list of all the unique words extracted from the training corpus. And then we passed the tagged document as input for the doc2vec function in order to train the model. So the first parameters of the function is the document. Then other parameters are dm to define the training algorithms. By default, dm is equal to 1. That means distributed memory version of paragraph vectors. But like word2vec, there are two models for implementing doc2vec. So if you set default, if you set dm equals to 0, you can implement the distributed bag of words version of paragraph vectors. So finally, we will obtain with the docVect property all the train vectors for the document tag seen during the training. And its length is determined by the size parameter. So we set the vector size using the default value that is 100. So now I cannot show you with the picture all the features, but in this case, track name was replaced with 100 new additional encoded columns. Furthermore, we hypothesized that this variable could also be used to extract the language of the song and include it as additional features. There are several libraries to cope with this task. Unfortunately, we tried LangDetect and Guess Language Spirit that are two Python libraries with no limitation, but they have low accuracy and they are very slow with a big data set. Otherwise, TextBlob and Google Trans have high accuracy, but they have a limited daily request because they use the Google API to detect the language. Also, we have to say that song title is often too short and may not contain letters, but only numbers and or symbols. So as a matter of fact, for example, if the title of a song is 100%, what language is it? We cannot tell. So in this case, maybe we have to add an exception in the code in order to catch this kind of situation and handle them accordingly. Then we have the artist features, another document level features. Being a categorical variable with many levels, it could be encoded using leave one out techniques. This technique is very similar to target encoding. That is the process of replacing a categorical variable with the mean of the target variable values related to that category, to that level. But in this case, the techniques exclude the current row target value in the mean calculation. Then we have the date features, that is a query level features. The date could be divided into multiple columns, describing here month, day, and we can use it to extract the week of the day. Weekday range from 0 to 7, that means from Monday to Sunday. Especially months and weekday can be quite useful in understanding periodicity and seasonality of the event, for example, summer song or Christmas song. And then we decide to remove the here because going into the future, if we pass now the here into the model, it would not match the one used to train the model. So we decided to remove because maybe it's not a useful features. And finally, the region, our query, we manipulate it through the pandas factorize function that helps to get the numeric representation of the array by identifying distinct value. So this is our final data set after the data preprocessing, where all the features have been transformed into numerical vectors. This is an example where we applied the hash encoding techniques and we use the relevance label from 0 to 20, as you can see from the ranking column. The stream feature was kept like it is, it was already numeric, while the ID, so our URL feature encoded, was used to train, was used for the data preprocessing part. So if you remember, to handle the missing values. But then it was removed from the training set data, since as document level features would not be a great help for the relevance. Now we can start with the model training part. We decide to implement learning to rank using one of the most widely used open source library called XGBoost. It is an optimized distributed garden boosting library designed to be highly efficient, flexible, and portable. It implements machine learning algorithms under the gradient boosting framework, available for Python or other programming languages. It is open source, and it supports both pairwise and listwise models. Both building and evaluating models can be computationally expensive because, as explained above, we need to provide the proper data set where each feature is a numerical aspect. When the dataset is ready and well structured, we have to split the entire dataset in two parts, the training set and the test set. Training set is used to build and train the model, while the test set is held back and used to evaluate the performance of the model on unseen data. In this phase, we have to be sure that a certain amount of sample for a given query are present in both sets, and then I will explain you why. We then separate the relevance label column, the query column, and the training vectors in different components to create the XGBoost matrices, necessary structure to train the model with XGBoost for both memory efficiency and training speed. So this is the Python example code about what described so far. I mean, with the first line of code, I removed from the data set, from the data frame, these three columns: ranking, ID, and query ID. Training query ID column is the column that contains all the query IDs from the input data frame. Training query groups means the value count for each query. And training label column is the relevance label column. So we use this component to create the XGBoost matrices. And label is our target variable. The same things was done to create then the test set. So now we can train the model using lambda-mart method. Lambda-mart is a combination between lambda-ranked and mart algorithms. The model performs list-wise ranking. So this approach directly looks at the entire list of documents and try to come up with the optimal ordering for it. To measure the output of models, we use a metric called normalized discounted cumulative gain. And the evaluation measure is then an average across the query. I mean, first of all, the NDCG is calculated for each query. And then the model calculates the mean across the query to obtain one final result. Here is the code example to show how to implement lambda-mart method. If you check the XGBoost documentation, you can see that there are three methods of ranking. They all use the lambda-mart algorithms, but what changed is the objective function. So if you see, our objective is rank column NDCG, because we use the NDCG as evaluation matrix. And in particular, we use the NDCG at 10 that corresponds, that consider only the first 10 results in the search result list. And then we save the model in a JSON format. There are several metrics which are commonly used to judge a learning to rank algorithms. DCG and its normalized variant are usually preferred when multiple levels of relevance are used. So we know that the goal of the model is to optimize the ordering of items, in our case, song, for a particular query. So what is important is the song ranking position among all the other songs. DCG aims to evaluate whether the model is able to return the most relevant document in the highest position of the search result list, and the least relevant document in the lowest position in descending order. So the idea behind DCG is that highly relevant documents in a lower ranked position of the search result list should be penalized. And so relevance value is reduced logarithmically proportional to the position of the result. The corresponding normalized metric, NDCG, is obtained dividing the DCG by the ideal DCG. That means the DCG of the best possible ranking. So when the search result list is perfect, as you can see in the ideal column in the table on the side. And the NDCG matrix is a normalized matrix, so it will be in the range from 0 to 1. So this is very important to understand, because when we are creating our training and test set, we have to be sure that we are using realistic set of samples, and we must have a balance of sample per query in both sets. So we should avoid these common mistakes, and we have to pay attention to two possible conditions that can potentially skyrocket the NDCG average. One condition is one sample per query group. So for example, in our case, if we have just one song for the query Spain. In this case, the NDCG will be 1, so will be perfect. And independently of the model, the average will increase in a misleading way. So it's better to remove this query. The other condition is one relevance label for all the sample in a query group. So in our case, maybe for example, for the query Spain, we have only song with the same relevance, with the same position. And also in this case, it's better to remove this query, because the model will not understand, will not learn anything. And then finally, I will show you the result obtained. In our case, as mentioned earlier, we use the NDCG at 10, where at 10 denotes that the metric is evaluated only on the top 10 song, top 10 documents. We summarize in this table the NDCG at 10 values obtained after the model training. Actually, we created 4 different models. So with different type of encoding of the track name features, and with different way of grouping the position values. So relevance label from 0 to 10 and relevance label from 0 to 20. We can see that the model with the best performance, so the best eval NDCG at 10, is the model where we applied doc-to-vec encoding and relevance label from 0 to 20. The eval NDCG at 10 is 0.82. So finally, our conclusion: data preprocessing and feature engineering are crucial and the most important step to adapt a learning to rank project to a real-world scenario. They are the most important part, but also the most expensive part in terms of time and resources. Language detection could be easier if we had available the lyrics of the song, and adding the language as additional features could be useful to improve the model performance. We could also use this feature to create a query document level features and check the correlation between the country and the language of the song. So the model where we have used doc-to-vec techniques and the relevance rating from 0 to 20 is the best model in terms of performance. The differences with the other models are very small, so we cannot tell exactly the reason of why it performed better than the other. But it will be interesting to evaluate them online to see if they are actually very similar as they seem, or if there is some difference online that the offline evaluation could not identify. And then a further study could be conducted using the library TreeShep that gives an explanation to the model behavior, and in particular, how each feature impacts on the model output. So thank you for our attention.
Thank you, Ilaria. So as we've done for Luke, if you have any questions, please write them in the chat, and we are going to address them in order. In the meantime, you can raise your virtual hands to clap Ilaria's job. Very nice presentation, by the way. So let's see, let's wait like a few minutes if there are any questions. And after that, we are going to just leave some time for other questions, more general related information retrieval, Apache Solr, Elasticsearch, and whatever you may be experiencing. So we have a question from Andrew in the meantime. So over to you, Andrew. You can unmute yourself.
I just wondered if you've done any significance tests on the results.
So significance from which perspective, Andres?
Well, okay. So normally, when you look at the results between two things, you look at if there's any significance between them. There are various types of significant tests, like t-tests, for example, which are commonly used these days to examine the difference between usually average precision. Although I have to say I've not seen any. I'm not sure I've seen any significance tests on normalized discounted cumulative gain. I just wondered if you've done any significant tests, because certainly from what I see, looking across the row, it didn't seem to be that much of a difference.
Okay, so Ilaria may elaborate a bit more, but so from a statistical perspective, right, Andrew?
Yes.
And
but
as far as I know,
I
no,
can't
right?
understand what you mean with a significant test.
I guess comparing like populations, but anyway, I think the short answer is no, right, Ilaria?
Sorry?
The short answer is no. You have not done any significant test for this experiment.
No.
Okay, thank you.
So we have a second question from Ben. So over to you, Ben. You can unmute yourself and over to you, Ben.
Yeah, hi, thanks.
You can unmute yourself.
Yeah, can you hear me? I don't know if you can hear me okay. Great, hi there. Thanks for the presentation and yeah, thorough explanation of the process to get an XGBoost model. I was wondering if you could explain maybe the choices you made in doing, sorry, I can't remember if you did pointwise or listwise. Why would you go for that approach, and did you consider doing, say, pairwise, which, as you say, is also a feature of the Lambda Mart? Thank you.
Thank you, Ben. I'll pass to Ilaria, but I think a short answer, and then Ilaria, if you want to add anything, you can. A short answer is we did use Lambda Mart, and we've mostly listwise approach every day, and basically we have not compared it with the pairwise approach. The main reason probably was just that taking a look into the literature, we saw that is more promising to use Lambda Mart in that way, but we may be wrong. We haven't explored that much in detail. Ilaria, I don't know if you want to add anything.
No, we didn't explore the pairwise, and we have used the DCG and the NDCG because usually we're preferred when multiple levels of relevance are used. So we decide to choose this the listwise instead of pairwise or pointwise. But
yeah, I just wonder if
instead of pairwise or pointwise.
Yeah, I wonder if pairwise would tell you more about, you know, the way that songs are played next to each other. If there's some, you know, some additional information that comes from it, but I really don't know. Yeah, I was just curious. Thank you.
We will consider that. Thank you, Ben. Okay, so we have Mohammed Reza. I was wondering to know. So over to you, Mohammed Reza.
Hi there. Can you hear me?
Yes.
Okay, great. Yeah. First of all, thank you very much for the great presentation. And my question is, actually, I wanted to know how the relevance scores were determined in the data set for each query groups. I wanted to know, was the decision was based on the number of the streams, or any other factors actually were considered? Thanks.
Yeah, the relevance score, the relevance labels were determined from the position on the chart. So we have grouped the position values to estimate the relevance score. But we put in our to-do list to check also by using the stream count instead of the position to check what changes and if the model performed the same or if there are differences. Yes.
Thank you very much.
Yeah, I can add on top of that, Ilaria has experimented with different grades as well. So from 0 to 10, from 0 to 20. In other projects, we have also experimented from 0 to 4, which is probably something you find more across like datasets, available datasets. But that was part of our investigation. So in the end, I think yeah, we got better results for the latter, right? For a little bit finer grain of relevance labels, which was interesting. Thank you again, Ilaria, for your presentation. If there's any other, so we have roughly 5 to 10 minutes. So if there's any other question about information retrieval problems and Apache Solr or Elasticsearch problems, related information retrieval tasks, feel free to write them in the chat and we can go over them and see if we can provide some help. So let's wait just a few minutes to see if there's anything. So when's the next meetup? We normally do them every 4 months. So that was the schedule for the on-site meetups. Now that we moved online, to be honest, as soon as we have some interesting talk, so even every couple of months or monthly, we would be able to organize them. We have in the queue a potential candidate from Rafa on a quite interesting talk for like detection of certain bad words in text and how this could affect the search engine. So we will keep you updated in the group. So normally 4 months, but we hope to reach like a little bit higher frequency from the online possibility. Absolutely, Ben. Feel free to send us an abstract with the title, and if it seems quite relevant to the topic of the information retrieval meetup. So definitely happy for that. Thank you. Okay, so this is actually another question on Ilaria's talk. So Ilaria, if you want to answer.
Yes, this is the sampling for training. So during the data preprocessing part, we decide to estimate the relevance label from the position, but we decide to group the position values because position values range from 1 to 200, and maybe and often the relevance label should be from 0 and at least from 0 to 5 or maximum 10. So we try these two different ways, from 0 to 10 and from 0 to 20, to check the differences. But we did this during the training part.
Yeah, and on top of that, Luke, just to give more detail. Actually, I mean, Ilaria explained that during the talk, but the dataset itself effectively was not born as a learning to rank dataset. So it was not a query document per list. It was basically data collected from like a sort of top chart, monthly, daily ranking. So the ranking of the song effectively was not the ranking of a search result list, but was a ranking in this sort of top chart based on, I don't know, popularity and streams and other.
Maybe the number of the streams, yeah.
Yeah, we don't know if it was just a direct correlation between the number of streams, for example, in that day, maybe, or whatever. And anyway, Ilaria will work a little bit more on that, also exploring the feature importance to understand, for example, if it was just the streamings, is the model capturing correctly this information, and why, for example, using doc2vec, we get a better NDCG. So possibly there are also other features involved in the original quotation ranking in the top chart. So basically we adapted the dataset to simulate a learning to rank problem, and effectively the dataset itself was not about a query document per list.
Yeah, great. That's a great explanation. Thank you. That's a very interesting use case you've got there. Thank you.
Probably we can wrap it up because I don't see any other questions. So it has been our pleasure to have you tonight and today, depending on the time zone. And please register to the meetup group. Probably all of you are already registered, and we are going to, of course, post news for new meetups we organize, and also with the recording. So we're going to publish the recording of the videos, and potentially also a blog post. I think Ilaria is working on a blog post summarizing her talk, so you will find more information there. So thank you very much for your time, and have a nice evening, day, all of you. Bye-bye.